My name is Carlos Baquero, and I'm going to present a mechanism for scalable, eventually consistent counting on a geo-replicated setting. The mechanism is called end-of counters, and this has been done jointly with Paulo Almeida. And we are both in the ASLA group in University of Minho. So we are targeting a setting where for a given system there is the intention to count given activities. So a typical example is the number of like clicks in a given subject in Facebook. And we are as stated, in a geo-replicated setting where we want to have users everywhere in the world being able to update account, and we also want to have more up-to-date as possible view of the current count everywhere. And since we are in a geo-replicated setting, we cannot rule out the possibility of partitions. So this is going to make the problem a little more difficult than it will be in other simpler settings. We are targeting at what? We are targeting at precise counting. So there are several mechanisms that provide probabilistic counting that have very interesting properties, but they cannot give a precise count on the actual number of counts. They give always an estimation with a given error bound, like a 5% error bound, for instance. So we are ruling out probabilistic approaches. As stated, we are in a geo-replicated scale, so we need to consider that we have high latency between some points, and we are having long distance links also between naturally distant points. As for partition tolerance, we want to tackle both partitions between data centers or within a data center, but also the partitions from a client or a client representing a stateless app into the server. And in this case, we want to support failover so that we can switch to another server if the server we are talking with fails. And we even want to support in the extreme disconnected operation. So in the case where we have this capability at the client, where the client itself is the app that is issuing the counts, we can also be able to model disconnected operation and register the counts locally and propagate them when possible when the partitions heal. Our assumptions over the network is that it is unreliable but non-Byzantine, and we will try to operate even directly on top of UDP with the possibility of losing packets, reordering them, and repeating them. We aim for scalability, both in the number of counting sources. So one big aim is to consider really large-scale counting endeavors where we have many counting sources, and we want to try to design it in a way that we can have a decent throughput. So this will lead us into multi-tier approaches. And what do we want to deliver in terms of how the counts are observed? We define some criteria that will allow us to define what is eventually consistent accounting. The technique can be generalized to several distinct counting actions, so we can be issuing number of flags for many distinct pages, but for the rest of the description we will, for simplicity, we will only consider a single distributed counter. Okay, so most people are already familiar with eventually consistent criteria and also with session guarantees. Here we specialize these notions to define what we call eventually consistent distributed counting. So the local user or the local app that is doing the counter, it can issue an increment operation, and it can also that increments the global count, and it can issue a distinct fetch operation that is going to consult the ongoing count. And these are the properties that we expect from the system with regard to the number of increments and the result of the fetch operation. So the first property, and this is can be related to a session guarantee property, is that a fetch can return at most the number of increments done so far. So we cannot return increments that have not been registered yet in the system. So this establishes a upper bound on the number of increments that can be returned. And now for the lower bound, we said that at a given node, a fetch should return at least the sum of the value returned by the previous fetch on that node, plus the number of increments issued by this node between these two fetches. So this means that if we return a count of 12 to a user, and later on this same user does 2 additional increments, then the next fetch that he does must report at least 14. So it must report at least the last reported count plus the number of increments that he knows that he did locally. And well, we want all the increments to eventually become known, and this is captured by the last property. So we said that at least all increments globally issued up to a given point in wall clock time will be eventually reported at a later time at every node. And in order to deliver this, we have some assumptions that must be met. One is that crashed nodes eventually recover with persistent state. So this forces the nodes to be a little more robust than usual. So they can be pictured as a CPU device with disk redundancy, for instance. And we also require messages to eventually go through. So we assume that partitions will eventually heal, and after healing we can pass messages. This doesn't mean that we require all the messages to go through. So we can have some messages permanently lost, but when partitions heal, we must have at least some new messages that go through the system. So before we get into the solution we are presenting, let's consider some simple designs, some preliminary simple designs. So this is the first design. We'll consider a single server in the cluster and FIN clients. So these FIN clients will just send messages that say +1, and these messages are communicated like through remote procedure calls to the single server. So we have many problems in this simple solution. One is that since we are operating at a geo-replicated setting, or geo-distributed in this case, we can have clients that are close to the server, so their RPCs will have a low latency. So we illustrate this by putting here 10 milliseconds, but we can have other clients that are in distant regions, and they will exhibit much higher latency across the globe. But this is not so. We have different response times for different clients. Another important obvious point is that we have a single point of failure. So if the server that is doing our count fails, we have nowhere to switch to. And this also limits throughput if we are considering high numbers of clients. So we can try to improve a little bit this design by considering still FIN clients connected by a classic RPC channel, but now we are replicating the servers. So we are replicating by using a CRDT designed, so a conflict replicated data type design that is known as a GE counter, where basically each server will have control over a given position in a vector of counters. So the vector of counters of integers is is as large as the number of servers that we have associated to this count we are doing. It does not need to be the whole the total number of servers in the data center, but a subset of servers that are replicating a given counting action, so the counts for a specific page. So each server has control over his own count, and we are depicting this in bold in the figure. And it also has a vision of the counts that have been registered in other servers. So now we can have clients connect to the servers that are closer to them, if we assume that we place the servers in different regions in the world. So they can have all low latency connection to their respective server. And across servers within the core of the system, we are paying the price of high latency, but this is having no impact on the client to server interactions. So each client will supply his update to its local server, get a response, and then asynchronously the servers will do some entropy between themselves in order to take the pointwise maximum between their vector of counters. And this is the way that all the counts registered in different servers propagate to every other servers. So now we solve many problems. So we have some fault tolerance. We can switch to another server if server fails. We can scale this thing in the sense that we can add more servers to increase the throughput available to handle clients. And since clients can choose nearby servers, we are kind of addressing the long latency problem from some clients. But we still have problems with failover. So although I said that we have some fault tolerance, we still have problems with failover because we are doing a RPC connection that is trying to send a command that is essentially a +1, an increment command. And these commands are not idempotent, so this can get us into a difficult position in event of a failure, as we illustrate next. So we have this problem with non-idempotent commands that has been kind of coined as the call me maybe problem or the Jepsen problem. So consider this situation. So first a client opens a connection to server A, and we have kind of a stateless client, but that is able to keep say a TCP connection. Now the client sends a +1 instruction to be processed at server A, because his end user did a +1 on the entity, and now the connection time is out. So at this point we are not sure and cannot be sure if the +1 was incorporated on server A or if it was not incorporated on server A. So we don't know or if the connection timed out after delivering the message or before delivering the message. So the point now is, can the client switch to another server? Well, it cannot safely switch to another server unless he knows if the +1 was accounted to or not. And the only way to know this is to keep insisting with this same server and keeping the session alive with the same server, and this will probably rule out even the timeout. So we need to insist with the same server because this is the server that, looking at sequence numbers in the messages, can know if this message was delivered or not. If we switch to another server, we have a risk of having a double accounting. If we switch to another server and don't replay the +1, we have the risk of not having the +1 accounted. So we are into a situation where we can have the +1 or -1 in failure scenarios depending on which option we choose. So luckily this thing can be solved if we do the passing of countings with idempotent messages. This leads us to the third design. So now again we have multiple servers, but we have more states at the client side. So now the client has his own ID and he knows his position in a vector, so he can register the count locally in its own vector. Probably he will also have a vision of the all the counters in the vector so that he can report the global count to its end clients. But we are in the figure, we are not representing that vision. So the client can register an increase, say up to 34 in his local position in the vector, and now instead of saying add 34, it sends a message that says, okay, my position is now up to 44. And when this message arrives to the server, it is incorporated into the state of the server by taking the pointwise maximum between the received messages from the client and the vector that is held at the server. So at this example, we are not having entries per servers, but the servers are storing vectors on that depict the client increments. So the problem here is that the vector that is stored at the server, his length is proportional to the number of clients that are operating on the system, and this poses a big scalability problem. So again, we do this anti-entropy with the pointwise maximum between the servers, and eventually all the clients will get to see all the increments from other clients. But again, there is a big price to be paid, because if we have 1,000 clients, then we have servers that have vectors with 1,000 entries, and each client will also have a vector with this number of entries, at least in the simpler design. But this can be optimized, but cannot be optimized on the server side, and this is the problem. So we have some fault tolerance. Now we have failover because now there is no problem on switching to another server. We don't need to know if the message came through or not when switching, because the messages are idempotent, so we can replay them with no consequence on the different server. We have a decent local throughput because we can increment locally at the client. We don't need any communication step with the server. But we have limitations on server throughput in the sense that the server needs to store a vector that is proportional to the number of clients. And this has, of course, an impact on the scalability of the design. So we get into the last solution, which is the solution that we are designing here. So we look at now at the run with and-off counters. So now we have server-side G counter, as we used in the last two solutions. So we have as many counters in the vector as the number of servers. So we are addressing the scalability problem on the number of clients. So now the idea is to register the count locally at the client, but then find a way to transfer the count from the client to the server in a way that is idempotent but doesn't need to have one position per client. So we are trying to transfer amounts between clients and servers. So at this point, the client has his own count that was at 0. He received a local increment from its user, and now the counter at the client is at 1. So at this point, there has been no communication with the servers or with the cloud infrastructure, and this count is only known locally at the client. So it is important that the client has some redundancy in terms of persistence, so that if it crashes, it can recover with its state, with the state that it had before crashing. Now we don't want to keep these counts in the clients forever, so we want to communicate them to the server. And now we have these two arrows that say idempotent messaging, and basically what it says that we had several messages that were sent from client to server, server to client, etc. It's a total of 3 to 4 steps, and all these messages are idempotent. And in the end of these, what we call an end-off protocol, we have safely transmitted the count that was at 1 at the client. It was transferred to the server that moved it from 33 to 34. So now the client is again at 0, and we have communicated this count to the server side. And the same can be done with other clients. So the magic here is this idempotent messaging protocol that is able to transmit amounts from one place to another, in this case from a client to a server, in a way that is tolerant to partitions and that can tolerate failover. So assuming that this thing is possible, we have many important properties met. We have fault tolerance because we can switch servers, and related we have failover, and failover is safe because messages are idempotent. We can still choose nearby servers at the clients, and we have both local throughput because the increments are registered locally at the client, and we have also server throughput because you can even build a hierarchy that can distribute the load that is associated to these transfers. So we can achieve scalability to arbitrary sizes. And in order to have an architecture that is more prone for scalability, we really need to construct more tires. So now I'm just showing a more complex deployment of this system, and then I will get into details on the end-of protocol itself. That's where the relevant parts are. So we can look at tier 2, which has the end clients, and this tier 2 clients, the end client can choose any server from the middle tier, from tier 1, and do the handoffs to those servers. Those servers must be connected to each other because we want to support failover, and in case of failover we are communicating some amounts to a third-party mid-tier server that need to be communicated to the chosen destination server. This is why we are assuming these links between the mid-tier. And so the mid-tier servers will handle most of the load from the clients. And recall that the clients don't need to communicate an amount after each increment. They can accumulate some increments and only hand off when the counter has reached a given size, or from time to time according to some time to transmit value. And then the mid-tier servers can communicate to root servers, and the entries for the root servers are the ones that are going to be known everywhere. So in terms of state size, the system will have a state that is proportional to the number of root servers, where we have a standard gig counter between them. So tiers are enforcing ID containment. We will see that we don't propagate the ID of the end clients across tiers, and they are also distributing load. So recapping some of the properties that we are hoping here. So the user increments are issued on the local counter. So it depicts a very high response time. Nodes are communicating between themselves, and by nodes I say end clients, mid-tier nodes, and root servers, by exchanging CRDT replica states in messages. So all this communication is idempotent. So we are doing a migration of counts from source counters, ultimately at the user side, towards the destination counters and the counters that are kept at the root servers. And we do this without spreading information on the client IDs themselves. So we are avoiding structures in the system that are linear with the number of clients. And we do this with one-to-one interactions. So we are avoiding issues of group membership, and we are also avoiding a fixed penalty by that will be associated to running a replicated algorithm for keeping a consistent view of the count if you were like running Paxos or something. So now clients will be able to safely fail over to other servers, and our channel assumptions again can lose, duplicate, and reorder messages. So I give a quick vision on what state must be kept within the data types. So basically we have a node ID for each intervening node, and we have two logical clocks. One is the source clock that is incremented when creating tokens. The other is a destination clock that is incremented at a replica that is receiving a handoff when it creates a slot. We have a mapping from node IDs to integers, and we will try to keep this mapping only locally known, except for the entries that respect to root servers. And then we have these notions of slots, that is positions at the destination of the handoff that can be filled by a token later on. And then we have the tokens, that is a pair from source destination with the corresponding source destination clocks and the count that is being transferred. And because we also want to provide to clients a notion of how the global count is doing, we are also running an aggregation protocol that will allow reporting to the clients what is the global count. And for that we need to have two other variables plus the identification of the tire. But in the description I will not get into details on how this reporting is done at the clients. This can be checked later in the paper. So now we are getting into the core of the algorithm, that is the handoff protocol. So we are looking at a situation where we have a node I that is going to be the source node, the node that is transferring an amount towards another node, and we have node G, and this is a lower tier node that is going to be the destination of the amount that is being communicated by node I. So at node I we have a source clock at 2, destination clock at 0 says that it was not destination of any counts. We have the value of the counter that has been stored locally, so I is mapped to 9. This means that node I already received it from its user 9 increments, and we have no slots or tokens. In the destination node we have a destination clock already at 5, and it already stores a count that is at 1021, and no slots and tokens. So the first step is to send a message from node I to node J with its state. And now we can see that after node J receives this message, it merges the message with a appropriate CRDT merge procedure. And the result of merging this message is that it now knows that a node I communicated with him as a source of a transfer. So at this point he consulted the node I source clock, that is 2. He knows his own destination clock, that was 5. So he created a slot that is mapped to node I. So it is a slot for a transfer from node I. And this slot stores the source clock and the destination clock at slot creation. At this point it also incremented the destination clock to 6, so that if it later receives a communication from some other node, it will create a different slot. So simplifying, node J is now ready to receive a transfer from node I. But node I doesn't know anything about this yet, and for this we need to send a message with the state from node J to node I. This is what happens here. And now again the merge procedure from these two states is going to increase the source clock and create a token. So when creating a token at a node that is being the source of an handoff, it is going to transfer the amount under its entry, under the I entry. So it's going to transfer the 9 from its entry I into the token. But the token has a fixed destination and the clocks that identify it. So now the value that is stored locally is 0, and the 9 has been transferred into a counter, into a token. At this point, you can still consult with fetch, and we'll get the 9 visible there, and then the extra variables that we are not representing will make sure that these properties, these grow-only properties of the count are kept even after transferring the token. So now that we transfer the token, we cannot go back. We cannot. This token can only be removed if we communicate it with the destination node, that is node J. So this means that if now we try to communicate with node J and we fail, and we need to fail over, we are going to communicate this token to a third node, say node L, and it will be that third node, possibly a mid-tier node, that will have to hand over the token to the destination node. But we are just showing a simpler run where we can actually communicate again with node J. So we do exactly that. And now node J, in this merge procedure, he sees that there is a token with itself as a destination that is matching a slot that it has. Oh, and only in these conditions he is accepting the token. So a token can only be incorporated if it fills a matching slot in the destination. And this is exactly what happened in this case. So the value of 9 has been transferred into the counter of J, and now J is at 1030. And now for the final step, if J sends its state back to node I can see that the slot is no longer there. It can consult the clocks, and it can remove his own token. So an important outcome of all this interchange is that if we now look at the end states in both node I and node J, we can see that in node J there is no memory of an interaction with node I. So we don't need to store the name of node I in the state at this point. And the same thing is happening at node I. But this is especially important in the destination nodes, because we avoided having to store memory of the clients to which there were interactions. So after a successful handoff, all memory of the source IDs are removed from the system, and this is very important for scalability. So the memory of node I only exists transiently during the transfer. There are several steps in the transfer, but this can be pipelined, so we can be receiving new slots for a node while we are still transferring the tokens that were created for slots that have been received before. So although we have this appreciable number of steps, this can be pipelined. So we have given, well, high-level description of the handoff protocol, and in the associated paper it's possible to see how this can be integrated into accounting infrastructure across many tiers, and how the counting can be made available to the different nodes. But the one important thing to take in mind here is that the handoff protocol is not specific for doing distributed counting. So basically it's a protocol that allows it reliably transfer between two parties. It allows to reliably transfer an amount from a source party to a destination party. And for this, we want to be able to have some operations on the amount. We need to be able to sum the amount to the destination part. We need to be able to zero the amount on the origin part after we create the token. And we need to be able to to take pointwise maximums. So all these mechanisms can be generalized to technically any commutative monoid, but basically to any structure that has an appropriate way of doing the zeroing, the addition, and the maximum. And one particular case of such a structure is if we consider a map of keys of strings to counters. This is going to be a commutative monoid, and we can generalize these operations to this structure, generalizing it from a single counter. So now, if we can figure a structure like that, we can start designing, for instance, kind of bank accounts or wallets of PN counters. So PN counters are a different CRDT structure, where instead of storing a single count that is only growing, we store two counts. One count for the positive side, positive count, and another count for the negative count. So both of them are always growing, but the end amount is the result of subtracting the negative counts to the positive one. And this allows to make counters that can go up and down, but by resorting to two counts that only go up, the positive and the negative part. And if we have several PN counters, we can leverage this end-of protocol to do things like removing an amount from one account and at the same time adding that same amount to the other account by increasing the negative part on the source account and increasing the positive part on the destination account. And with these more complex data types, the end of protocol can make sure that these two actions, the withdraw and the deposit, take action at the same time along each replica that it is communicated to. So in a way, we kind of obtain some form of atomicity and isolation in a setting that is tolerant to partitions and that is always available. And by doing such structure, we are enforcing a global invariant, and that is that the global sum across wallets is preserved during the transfers, because we have this atomicity between the credit and the debit. So this is already an important property that can be directly obtained by the end of protocol. And if in addition we try to enforce locally that we cannot, suppose that we have a PN counter where we have 10 at the positive side and 0 at the negative side. So this means that actually we have 10 of credit. And locally we can allow removing money up to the point that the negative part becomes as high as the positive part, and at that point we can start denying decrement operation. So if we do this thing locally, making sure that the negative part does not get higher than the positive part, we are locally enforcing a non-negative environment. If we do it everywhere, we are globally enforcing also a non-negative invariant. So we are making sure that the balance across all the wallets doesn't get negative. And what can we do once we have established this local invariant? So if we have 10 and we have decremented up to 10, now we are no longer available to the user because we cannot accept more decrements. But at this point, if we have more fine control over the end of transfer directions, we can try to get money from the root levers if they are available in other wallets, and then this will increase our positive size, and then again we'll be able to decrement it. So this implies some changes to the protocol, but it's possible to enforce it. So this leads us into our final observation, is that now looking at these more general case of doing transfer of amounts between wallets, what we don't get here is a global order on the operations. But do you really need a global order? If we have the stable global sum, and we can also keep the non-negative invariant, maybe the global order for some applications is not so necessary. And by doing it this way, we can operate under partitionable settings, preserving availability. We do it by flexible one-to-one interactions with failover support, and we avoid issues of group membership that are specifically problematic in systems with a very high number of nodes. So this is it for the talk. If you are interested, we have a technical report on this that you can fetch in archive, and we also have a prototype implementation in Clojure that can be fetched in GitHub. And this is just an attribution to the photos that were used. Thank you.